Today I want to speak a little about the whole system of the, for example, a system for detection of the cancer in the lung. And first I will introduce some techniques for pre-processing step. Then I will go to the detection part. It has part, in this part we will have some candidates that we are not sure about these candidates are cancer or not. In the next step we try to, for example, reduce the number of the candidates, and after that, after this reduction, we will go to the classification and say, for example, we can say which one has which one is the, for example, the cancer and which one is not. The whole system, it has 4 parts. The first part is pre-processing. This pre-processing part start from the, for example, capturing the image from the device. It can be MRI, CT, PET CT, or different type of the medical images. When you capture the images, you need to, for example, doing some processing to create a image that, for example, the person can interpret that. And because your device of, for example, capturing the image does not work in the time domain, and for example they use this, some frequencies and send it through the body and receive the reflection of that, and based on that they create an image from the slide, one slice of the body. For example, if we have an MRI image, it's...
Excuse me, I have a question.
Yeah.
What's the difference between the, for example, MRI and
in the MRI, if I am mistaken, I'm not sure. In MRI we have, for example, I think for the CT is the X-ray. You, for example, have a device that can send the X-ray, and X-ray goes through the body and, for example, pass the body, and in the back of that we have some reflection, and based on that we decide, for example, what's the inside of the body. And we don't have, for example, the device that goes through the body and get real pictures. In the, for example, PET CT, in the PET CT we, for example, inject some radioactive materials to the body, and again we get the X-ray, and based on that we decide, for example, these radioactive materials, for example, goes through the some special tissue, and when we, for example, when the X-ray goes through the body, they have some interaction between the X-ray and for example, these materials, and we have for example, an image. And for the MRI, I forgot that. I will explain to you later.
you mean all of them are 3D?
In the image, the structure of image is some slices. For example, here is the neck, and the last one is for example, the end of the lung. For example, in the mid part, these two are the, for example, 2 parts of the lung, and here is the heart. And in the end, for example, we have a small end of the lung. Okay, for example, this top is close to the neck, and we have a lot of the slide of the body, a slice of the image that shows each part of the body. Then, for example, the thickness of this area it can be between 2 millimeters to 8 millimeters. For example, it shows for example, in the body, this image is not, for example, for the one plane that there is no thickness. We for example capture all of the reflection of the body to the, for example, thickness between 2 millimeters or 8 millimeters of the body. It's based on the device that you will use. Yeah, and let me continue. For example, if we have one slide, it's something like this, and we have a noise in the device. If, for example, they will check, for example, for the metals or something, because it's created some noise, but still we have some noise in the image, because the image is originally in the frequency domain, and when we, for example, capture, and there is always noise. After noising or improving the contrast, because the contrast is important. For example, if we have a city image, we have a certain level of the, for example, the value, for example, between minus 3000 till minus 900. It's, for example, the air, and for example, for the bone is something between 500 to 1100. And based on the, for example, this value, we can, for example, saying which part of the, for example, this image is the lung, or, for example, bone, or the tissue between the lung. Or after pre-processing and prepare the image, we have a detection part. In the detection, we, for example, candidates some points and some area. It can be 2D or 3D in the lung, as a, for example, tumor. And there's a lot of techniques for example, candidate detection. For example, there is some rule base, as I said before. For example, what's the for example, the bandwidth of the bone, and for example, if we have for example some intensity between A to B, this is the bone, and for example we can set up a rule-based system, for example, to start to do segmentation and find some area, for example, in the lung. If we have some intensity is high, it shows there is something wrong, and it creates some for example, alarm, and after that we must go through that alarm and see what happened there. And there is, for example, some neural networks, and if you remember in the previous I don't know how many, but I think 2 or 3 discussion, we go through the RX algorithm. It was for the anomaly detection, and we apply that for the detection part for the cancer. After detection part, we have some candidates. These candidates, they are all of them are not the real tumor. Some of them are noise. Some of them it's the ordinary nodule in the lung, and we must go through the another part is false detection, a false reduction, false positive reduction. What's the meaning of the false positive? For example, if we know this area is the tumor and we mark it as a tumor, it's a true positive. If we have an area that we know is the tumor, but we needs to detect of this part is a false negative, and for example, if we mark that some area that is tumor but is not really one, this one is a false positive. And when we go through the lung, we will have a lot of false positive, and in the next step, after finding some candidates, there is a lot of techniques that try to reduce the false positive reduction.
SOAVE.
False.
False.
And false negative is that you couldn't find.
False negative, for example, if there is a tumor, and we didn't mark this one, is a false negative, because really it's not negative, and we false detection of the something negative, and it's a false negative. And I said the true, yeah. And this is something like this, for example, plus minus false. And false positive is this area. This one we wanna find all of our detection in here, but unfortunately we have a lot of things here, and we try to reduce the number of the candidates in the false negative.
And why you didn't try for example, false negative or true negative?
Yeah.
They are not important?
No, because it's a negative and it's true, and we know there is nothing, no tumor, for example. There is no nodule that is, for example, need to, for example, more research on that, and we are not interested to detect those parts. And after false positive, we reduce the number of the candidates, and now we can start to classification. And this is the process that the people doing, for example, for finding the probability of the cancer in the one set of image. And we have some idea about, for example, how to, because we have the RX algorithm, we implement RX algorithm here and try to detect some candidates, and now we have some idea here. After checking the false positive in the RX algorithm, we find out the location of the false positives. They are in some areas that it's easily to, for example, detect those points which are not valuable for the next steps. And we have some idea to, for example, add one new stage here, which can, for example, receive the result of the detection, and we can, for example, add some prior information to this part, and based on that we received some feedback from this part to the detector, and change the parameter of detector based on the, for example, this prior, and what's the detection, and some training steps that, for example, we can train the system in some, for example, test images, training sets, and for example, train this set, and after that we add the information of this part to the, not for the false positive reduction, but to, for example, add to the both of these two steps, both false positive reduction and classification. Because in the classification, if we know, for example, we have some area, this information that we thinking that this can be, for example, a graphical model of the lung. For example, it can be a 3D factograph of the lung that we put the prior of the, for example, some point in the lung that, for example, we know they are critic for the cancer detection, and if we have something close to that area, we can, for example, change the parameter of the detector. For example, the detector first can do some rough detection and put the result in this system, and we have some prior, and when we saw, for example, some alarms, some anomaly, again we can send the, for example, the area, the interested area with the new parameters, maybe with the different technique of the detection, and for example, increase the resolution of the detection in the critical area and decrease the resolution of the, for example, detection in some another area, improve the speed and accuracy. And also we have some idea here for pre-processing, and it will be the main part is for Nafisa for example, because she doing some techniques for the super resolution and denoising, and we discuss, and I think we can do something here, for example, to find the similar blocks and remove the same noise from those blocks and improve the result of the detection.
I have a question. At the end of the classification, if you just found that your classification total is not true, for example, some part just classified all of them, but some part is not true. For example, this part, the part 1 is exactly the part 2, should be in the part 2. So how you can just say that this problem is from the which step?
Really, when we go to the classification, we have, for example, the set of the candidates. For example, there are some nodules in the lung, and the goal of the classification is, for example, detect the stage. It can be detect of the stage of the cancer, or because we have different techniques for example, facing to these tumors. Maybe there is some techniques that need to some sample of the body, and the aim of the classification is, for example, we saw something and they are small or they are not important. It's not necessary, for example, to use some sample of this tissue, and we, for example, use the images with the high resolution images, or use for example, if we get a CT image or MRI image, we can go to the, for example, CT, PET CT, or the techniques that the image has a more resolution, or there's some techniques that, for example, use some proteins in the blood to, for example, detects for example, there is a cancer or not, and we can go through for example, next steps. But in the classification, we want, for example, detect what's the stage of the cancer. For example, needs to more using some drugs to, for example, reduce for example, the growth of this node. And I hope I answered your question. And for my for example, the next step for my research, I selected some techniques that some people use them for false positive reduction. For example, they use the anatomical information of the body, some fuzzy modeling of the lung, or Bayesian modeling, but it's not a new one. It's old technique and only use the Bayesian modeling for the classification, not for false positive reduction. And I select two of them to compare and use the, for example, false positive reduction and compare the result with our RX accuracy. If you have any
question, how can you evaluate your algorithm? I mean, maybe it have the possibility that it's real positive, but you didn't detection.
Really, there is a subset of, for example, CT image or MRI image that there's, for example, a public database that some expert person goes through the database and marks some point of that as, for example, cancer. And we, for example, can use the, for example, the detection, the person detection as the ground truth and apply our techniques, which we can apply in some of those images and see what's our detection and what is the real detection, and compare and find what's the percentage of that. And for example, for RX, we apply in the LIDC, it's a public database, and we detect all of the cancer tumor, but we had a lot of false positives. And also there is another big database in the University of Cornell that it's a database about how tumors response to the, I think, the drugs. Yeah, it has a lot of set of the image in the different time of one person. For example, one now, for example, one of them is for 1 year ago, another is for 6 months ago, and one of them is for now. And you can, for example, do a detection because we know where is the cancer, and we can, for example, apply our detection on each set, and for example, the shape of the cancer or nodule it's obvious or marked in the database.
I think the third part is kind of look at pre-classification.
Yeah, it can be as pre-classification, and also, yeah, it can be a pre-classification, and we can do something else here. For example, if is that when you wanna, for example, find the nodule is the cancer or not, is that there's a lot of parameters. For example, one of them is the shape, one of them is the growth of the, for example, nodule, for example, the duration of the time, for example, percentage of the fats in the, for example, nodule. And some of them you can, for example, check by image, but some of them is not possible. You need the exact sample of the tumor. And after detection, we want to, for example, estimate some of those properties of the nodules. And if, for example, you have a set of changing, for example, you know from time t1 to time tn, there is some changing in this way, it will be helpful to, for example, detection or find out what is the stage of the cancer.
Have you do the experiment or test image and get the rates of how many you select correct?
Yeah. we test our technique in the 12 sets, and we detect all of the cancers, but the ratio of the false positive to the true positive, the ratio of the true positive to the false positive, I think it's around 30%. It means 30%. It means, for example, if you select, you detect a cancer, you have at least 2 points that is not cancer. For 1 point that is true cancer, we have 2 points that is false positive.
I think for your application in medicine, I think your algorithm should be more aggressive. More aggressive. I mean, just we can get a lot of false positive.
The false positive
should
is
not miss the true positive.
Yeah, in the most of the detection techniques, they accept the, for example, the high percentage of the false positive, because if you have a lot of false positive, for example, you can test and find out it's not true. But if you miss a true positive, it's dangerous. And because of this, they, for example, set the parameters in some area that they will be sure that they will detect all of them, and if they have, for example, some false positive, they go through the another, for example, part and start to, for example, reduce some false positive and improve the result.